Welcome back. So, in the last lecture I discussed the concept of immunization in a lot of detail, and then I went on to take up the concept of key rate, duration and bucket exposures. Today I start with the final topic in bond analysis, and that is the term structure of interest rates. Now, this particular term I have already introduced a couple of times during the discussion on bond analysis, bond valuation rather. It represents the functional relationship between the maturity of the instrument, maturity of the underlying instrument or the interest rates and the interest rate themselves. In other words, if you go to a bank and you make a deposit of 1 year, you get a different interest rate from the interest rate that you would get if you make a deposit of say 10 years. So, this phenomenon whereby the interest rates vary in relation to the maturity of the bond is called term structure of interest rates. The allied concept of yield curves is the graphical depiction of this term structure of interest rates. In other words, the yield curve is simply a representation of the term structure. It presents the various types of interest rates, may be spot interest rates, may be par yields, may be the forward yields, but it presents the yields for different maturities. So, we will take the concept in detail now. The term structure I have already introduced. The term structure of interest rate refers to the yields on similar securities or interest rates with different maturities. So, that is called the term structure. The functional relationship between the maturity and the corresponding interest rate is called the term structure. Now, there are different types of yield curves. We have the spot yield curve, the par yield curve and the forward yield curve. Each of these yield curves represents or is a diagrammatic representation of the interest rates corresponding to different maturities. So, now we talk about the spot yield curve. We know the spot rates. How do we define the spot rates? We define the spot rates as the YTMs on 0 coupon bonds of the relevant maturity. I repeat, we define the spot rates as the yield to maturity on 0 coupon bonds of the relevant maturity. Therefore, the spot rate yield curve, or which is also called the spot curve, abbreviated as the spot curve, depicts the YTM of 0 coupon bonds of similar risk and of different maturities. So, we take the maturities along the x axis and take the yields along the y axis, and we calculate the yields corresponding to different maturities on the basis of the current prevailing prices of those instruments, 0 coupon bonds, and then we plot them against the maturity to get the yield spot yield curve. I repeat, we from the price information of 0 coupon bonds of different maturities, we work backwards, we work out the YTM, and then using that YTM and the maturity to which that YTM relates or the underlying instrument relates, we work out a curve. This is called the spot yield curve. Now, the YTMs of 0 coupon bonds is determined solely by maturity and price, because there are no intermediate coupons, there is no coupon payment. By the name itself, one can infer that 0 coupon bonds involve no coupon payments, there is only a single payment at maturity. Either the bond may be quoted at discount to face value and redeemed at face value, or it may be represented at face value and redeemed at a premium to face value. In any case, it does not really matter. The YTM of that bond will be determined by the maturity of the bond and its current prevailing price. So, YTMs of for each such security is determined by using the price, as I mentioned just now. Using the price, we work backwards, we work out the YTM, and then we use the YTM to plot a curve between the YTM and the maturity to which that YTM relates. This curve is also called the 0 curve or the strip curve, because the 0 coupon bonds are also sometimes called the stripped bonds. Now, similar to the spot curve for 0 coupon bonds, we can have the yield curve for coupon bonds, in which case a yield curve is plotted between the YTM of the coupon bonds and the corresponding maturities. You take the YTMs of various bonds, say maturity 1 year, 2 year, 3 year, 4 year, these are coupon bonds, and on these coupon bonds we work out the YTM on the basis of the current market price, the currently prevailing market price, and then we plot a curve between the YTMs and the maturities. For example, we have the 1 year T bond, the 2 year T bond, and so on. So, this is another example of a yield curve, but here we are using coupon bonds instead of the 0 coupon bonds that I talked about earlier, and which is usually called the spot yield curve or the spot curve. Now, it's important to mention here that the YTMs will not depend on the coupon rate, since the prices will adjust corresponding to different coupon rates, keeping the YTM constant. Actually, the YTM is determined by the riskiness of the bond. It is the market's perception of the riskiness of the bond which manifests itself in the YTM. A more risky bond where the cash flows from the bond are risky, or the realizability of the cash flows of the bond is suspect, would quote at a higher YTM, whereas bonds such as treasury bonds or government bonds would be quoting at a lower YTM, because they are very close to being riskless, and therefore, they would the risk premium thereon would be minimal. So, that is the main thing. The coupon rate themselves will not determine the YTM. The YTM is determined by the riskiness of the bond, and if the differential in coupon rates, for example, if you have a 10% coupon bond and a 20% coupon bond of the same risk level, then the prices will adjust themselves in such a way that the YTM of both the bonds turns out to be the same. So, yields are calculated for several maturities, and yields for bonds with maturities between these bonds are estimated by linear interpolation. So, this is a procedural issue. We have discrete points for different maturities, and if you want to work out the YTM for an intermediate maturity, say 3.5 years or 3.6 years, you do it by linear interpolation. This is the example of a yield curve. You can see here it is flat at the near end, and again it flattens out in the far end. In between it is rapidly sloping or highly sloping, otherwise it is flat at the both the extremes, the near end and the far end. In other words, what we infer is that for short maturities the fluctuation in interest rate with maturities is small, and similarly for very long maturities the same is the case. The fluctuation in interest, the changes in interest rates are very small compared to or with reference to the maturities. However, for intermediate maturities we find that the interest rate change rapidly with the increase in maturity, and the interest rates increase with the increase in maturities. So, this figure represents, the previous figure represented a yield curve for coupon treasury bonds constructed from yields on 1 month, 3 months, 6 months, 1 year, 2 year, 3 year, 5 year, 7 year, 10 year, 20 year and 30 year securities. So, yields are expressed on a semi-annual bond basis. So, this is what this particular figure represented. It is a yield curve of treasury bonds, coupon treasury bonds. On determining spot rate, this is an interesting topic. You see, I mentioned just now that what we do is we use the price, we take the price of the 0 coupon bond, the currently traded price of the 0 coupon bond, and on that basis working backwards, what we do is we compute the YTM of the bond, which is then plotted against the maturity of the bond. So, that gives us the various points along the spot yield curve. Now, it may so happen that 0 coupon bonds of certain maturities like say 3 years or 5 years or 10 years may not be existent or may not be trading in the market. In that situation, we have to extract the spot rates. We have to extract the spot rates out of the quotations or the prices for the relevant coupon bonds. This process is known as bootstrapping, and I will explain it with an example here. Let us do this example. This will illustrate the process of bootstrapping, whereby we determine the spot rates of various maturities on the basis of the prices. If the 0 coupon bonds of the relevant maturities are not trading, then we work out the corresponding spot rates on the basis of the prices of coupon bonds using this process of bootstrapping. So, let us look at this example to illustrate this phenomenon of bootstrapping or the process of bootstrapping. The cash prices on 6-month and 1 year treasury bills are 94.0 and 89.0. The face value is 100. A 1.5 year bond that will pay coupons of 4 units every 6 months currently sells at 94.84. A 2-year bond that will pay coupons of 5 units every 6 months currently sells at 97.12. We have to calculate the 6 month, 1 year, 1.5 year and 2 year 0 rates. All rates are continuously compounded. So, this is the problem. Let us read the problem once again. The cash prices of 6 month and 1 year treasury bills are 94 and 89, face value is 100. 1.5 year bond, again face value 100, that will pay coupons of 4 units every 6 months currently sells at 94.84, and a 2-year bond, again face value 100, that will pay coupons of 5 every 6 months currently sells for 97.12. We have to calculate the various spot rates. Now, as far as the 6 month and the 1 year rate is concerned, it is a straightforward exercise. We can work out from the T-bill quotes, because these are 0 coupon bonds. So, we do not have to manipulate anything. We can simply use these prices. Working backwards, we can calculate the YTM on these bonds, and on the basis of this we work out the spot rates for 6 months and the spot rate for 1 year. This is done here on this slide. The 6 month rate is because this 2 factor appears here to account for the annualization. This 2 factor here appears for annualization, because we work out the 6 month rate and we multiply it by 2 to get the annual rate. So, log of P1 upon P0, that gives me R for the 6 month period. I multiplied by 2 to give the R, to get the R or the YTM for the 1 year period on a bond equivalent basis. That comes to 12.38% for the 6 month bond, which is quoting at 94. Similarly, the 12 month or the 1 year spot rate is given by, now because this is a 1 year rate. So, we do not have to multiply by 2 here, log of 100 upon 89, which comes to 11.65%. For the 1.5 year, now please note here, we do not have the spot rate for 1.5 years, because we cannot have it directly, because we do not have a 0 coupon bond with a maturity of 1.5 years. We do not have a say treasury bill or a treasury bond which is a 0 coupon bond with a maturity of 1.5 years. So, we have to use the information encoded in the coupon bond to and extract the 1.5 year spot rate. Let us see how we do it. For the 1.5 year bond, we have the following equation. What will we receive from this 1.5 year bond? Assume the face value to be 100. We will receive 4 units of money at the end of 6 months. We will receive another 4 units of money at the end of 12 months, and then we will receive 104 units of money at the end of 1.5 years. So, we have to discount these 3 cash flows, and we are given that the current market price of the bond is 94.84, and therefore, we equate it to 94.84. We assume that the 1.5 year spot rate is R, and on that basis we discount all these 3 cash flows. We know the 6 month spot rate, we know the 12 month spot rate, but we do not know the 1.5 year spot rate. We assume it to be R, and then we discount all the cash flows, 6 month, 12 month and 1.5 year cash flows, and equate the aggregate thereof to 94.84 and calculate the value of R. That is precisely what is done here in this slide. The first 4 figure is discounted for 6 months, the second 4 figure is discounted for 1 year. Please note the rates are already available with us. The 6 month rate is 12.38%, the 1 year rate is 11.65%. So, we have the 6 month rate of 12.38%. That first cash flow of 4 is discounted at 12.38%, the second cash flow is discounted at 11.65%, and the third cash flow of 104, which occurs at t equal to 1.5 years, is discounted at r. And when we equate this to the current market price and solve the expression for r, what we get is r is equal to 11.5%. So, this process is called bootstrapping, where we extract the spot rates from the information given for the various coupon bonds which are traded in the market. You see, what may happen is, important thing is, what may happen is that we may not have 0 coupon bonds trading for all the maturities that are required for construction of the yield curve, and therefore, we have to, whatever 0 coupon bonds are available, as in this example we have the 6-month bond and the 12-month T-bills, we use directly and work out the spot rates. But for the instruments of maturities more than that, or for which we do not have 0 coupon bonds, we make use of this process of bootstrapping. We extract them from the coupon payments or the timing of the coupon payments using the spot rates which are available, and on that basis we work out the unknown spot rate by equating it to the current market price. The same exercise is done for the 2-year bond. Now, we have the information about the 6-month rate, we have the information about the 1-year rate, and we have the information about the 1.5-year rate. So, again, equating the present value of future cash flows, assuming the 2-year rate to be r to the current market price of 97.12, we work out the value of r, and we find that it is 11.3%. Now, we come to another concept, which is the par bond yield curve. What is par yield? We need to understand what is par yield. Now, par yield is the coupon rate on a bond. Let us say we are given a bond of given maturity, say 5 years. Then the par yield is that coupon rate at which the bond, the DCF value or the intrinsic value of the bond, or the theoretical market price of the bond would be equal to its par value. And so, let me explain again. If we have a bond which has a maturity of 5 years, then how will we work out the DCF value of the bond? We shall discount the coupons that are being paid at, let us say it is an annual coupon bond. We shall discount the coupon payments at t equal to 1, 2, 3, 4 and 5 plus the principal at 5 at the relevant spot rates. And now, we assume that coupon to be unknown, we use the given spot rates, and we equate this to the face value of the bond, that is the par value of the bond. And on that basis we get an equation for the coupon rate, and the expression that we get for the coupon rate, the number that we get for the coupon rate is called the par yield of the bond. So, because for a par bond the coupon rate must equal the YTM, so we can alternatively state this par yield as the YTM of a bond, of a par bond, of a bond that is quoting at par for each maturity. Both these definitions are equivalent, because for a par bond which is a level coupon bond redemption at face value, then we must have C is equal to Y, that is the coupon rate must be equal to the YTM. So, whether you define the par yield in terms of the YTM or you define the par yield in terms of the coupon, it comes to the same thing. So, let me repeat once again, the par yield on a bond is that coupon rate such that the quote of the bond or the market price of the bond is worked out on the basis of the discounting of future cash flows at the relevant spot rates works out to its par value. So, a par bond yield curve or par curve is not calculated from yields on actual bonds, but is constructed from the spot curve, which I shall show the formula just now. This is the formula here. We have a bond with a maturity of capital T. It is an annual pay bond, and the spot rates for 1, 2 and T as maturity are respectively S01, S02 and S0T. Then the coupon rate C, which solves this equation, which makes the present value of future cash flows equal to the par value, is called the par yield. As you can see here, in this expression the only unknown is C, the coupon rate, which equates the right hand side, that is the present value of all future cash flows discounted at the relevant spot rates equal to its par value. Now, I repeat, because for a bond quoting at par the coupon rate is equal to the YTM, we can also say that it is the YTM of a par bond of the corresponding maturity. Let us do an example to illustrate this concept. Suppose the 6 month, 12 month, 18 month and the 24 month 0 rates, that is the spot rates, are 5%, 6%, 6.5% and 7% respectively. What is the 2-year par yield? Let us assume, please note, in this case the coupon payments are semi-annual. So, if the coupon rate is C, the coupon payments are C upon 2. So, we shall receive C upon 2 at the end of 6 months, C upon 2 at the end of 1 year, C upon 2 at the end of 1.5 years, and then we shall receive the face value, that is 100, plus C upon 2 at the end of 2 years. And accordingly, all these figures are discounted at the corresponding spot rates. We are assuming continuous compounding here. So, we discount all these cash flows of C upon 2 at 0.5, 1.5 and 100 plus C upon 2 at t equal to 2. We are discounting all these at the relevant spot rates, 5% for the 6 month discounting, 6% for the 1 year discounting, 6.5% for the 1.5 year discounting and 7% for the 2 year discounting, and we equate this to the par value of the bond, which is 100. We are assuming it. You see, the par yield is independent of the face value of the bond. So, we assume it to be 100, and on that basis we find the value of C to be 7.072%. On solving this equation, we find that C is equal to 7.072%, and so this is what is called the par yield on this particular bond. And this is an interesting exercise. When the 0 curve is upward sloping means as you increase the maturity of the bond, the interest rate increases. As you increase the maturity of the bond, the interest rate increases. The 0 rate for a particular maturity is greater than the par yield for that maturity. Let us assume that you have a bond of a maturity of 2 years. Then what it says is that the spot rate for 2 years will be greater than the par yield of for 2 years. In other words, it would be greater than the YTM of a bond with a maturity of 2 years and which is quoting at par. So, we have a bond which is quoting at par, and we have to show that the YTM of that bond is less than the spot rate for 2 years, assuming that the curve is upward sloping, the yield curve is upward sloping. Now, the inference is quite straightforward. I had shown in an earlier lecture that the YTM of a bond must lie between must be sandwiched between the minimum spot rate and the maximum spot rate. Here, because the yield curve is upward sloping, the maximum spot rate will correspond to the higher maturity compared to the minimum spot rate, which will correspond to a lower maturity. So, the YTM must necessarily be between these two figures, the maximum spot rate and the minimum spot rate, and I repeat, because of the upward sloping nature of the curve, the maximum spot rate will correspond to the higher maturity, and therefore, the YTM will be less than the spot rate for the higher maturity. The inverse would be case in the case of a downward sloping curve. Now, we talk about forward rates. Now, forward rates are yields for future periods. Let me explain it briefly. Suppose today's t equal to 0, please recall the definition of a forward contract. What was a forward contract? A forward contract was a contract which was agreed upon at t equal to 0, which was negotiated at t equal to 0 as to all the relevant terms of delivery, that is the price, the date of delivery, the manner of delivery, and whatever the case may be. But the actual delivery, payment of price and all the issues relating to the settlement of the contract take place at a future date, which is also predefined at t equal to 0. We know the date of settlement at t equal to 0, and we also know the price and all other relevant things that are to occur at t equal to the maturity of the contract, which is the date on which the contract is finally settled. So, we have two dates, t equal to 0, where the negotiation of the contract takes place, and we have a date at which the the goods are delivered or the underlying is delivered and the price is paid, and but please note this time period T equal to capital T, which is called the maturity of the forward contract, is also predetermined. So, all the things are predetermined, all the things are agreed upon at T equal to 0, so that there is no ambiguity as to the settlement of the contract. So, that is what is a forward contract. The example that I have given you is of a commodity or a stock on which a forward contract is written, so that on the date of maturity you get or a currency, you get the currency US dollars or a stock or a commodity, and you pay the price at that particular point in time in the future. Now, what happens if instead of this underlying being a commodity or a stock or exchange currency, what happens if instead of these things we have a loan as the underlying or the interest rate as an underlying, or in other words what I am trying to say is, if as a T equal to 0 I agree with a banker that at T equal to 1 year I shall borrow say 1 million US dollars or 1 million rupees for 1 year from T equal to 1 to T equal to 2, but I want to protect myself against any change or any increase in interest rate during the intervening period between T equal to 0 and T equal to 1 year when the loan will start. I go to my banker and my banker agrees with me after negotiation that he would charge a certain rate which is agreed upon at T equal to 0 for a loan that is to be disbursed at T equal to 1 year, and that would let us say it would have a maturity of another 1 year or 2 years, whatever the case may be. Again, that will be negotiated at T equal to 0. So, all the terms relating to the loan, including the interest, the maturity, the repayment, whatever the case may be, are agreed at T equal to 0, and this is called a forward interest rate. The interest rate that is agreed upon as at T equal to 0 for a loan that is to be disbursed at a future date is known as a forward rate. So, forward rates are yields for future periods. A forward rate is a borrowing or lending rate for a loan that is to be made at some future date, as I explained just now. The notation one can go through. So, let us say I use the small f 1 2, that means a loan, this rate corresponds to a loan that is going to take place at T equal to 1, and that is going to be of 1 period, and it would be returned or repaid at T equal to 2. Similarly, f 1 5 would be a loan which is initiated at T equal to 1, the loan would be disbursed at T equal to 1, but the rate is determined at T equal to 0. Please note this, in all cases the rate is determined at T equal to 0, the loan is initiated, the loan is disbursed at T equal to 1, and the loan would be repaid at T equal to 5, and so on. So, this is the notation that we shall be using consistently in this course. The forward rate yield curve. The forward rate yield curve shows the future rates on bonds or money market securities for the same maturities for annual periods in the future. So, suppose you take a maturity of 1 year, the forward rate yield curve will give you the rates for loan say from the T equal to 1 year to T equal to 2 years, and then from T equal to 2 years to T equal to 3 years, T equal to 3 years to T equal to 4 years, and so on. This would be plotted, the rates would be plotted corresponding to these years. Now, here I have taken the maturity of the loan to be 1 year. You can have a forward rate yield curve for maturities of 2 years, but they would be quoted at 1 year intervals. So, you can have a forward yield curve for a loan of maturity 2 years, say the loan initiates at T equal to 1 and carries on up to T equal to 3 years. Then you can have the rate if the loan initiates at T equal to 2 and carries on up to T equal to 4 years. You can have a rate for the loan initiating at T equal to 3, carrying on up to T equal to 5 years, and so on. So, you can have different forward rate yield curves depending on different maturities of the underlying forward loan, and normally the quotations are on annual basis. So, even if it is a 5-year interest rate, it would be quoted for 1 year, 2 year, 3 years in the future. If the loan initiates at 1 year, if the loan initiates at 2 years, if the loan initiates at 3 years, and so on. Typically, the forward curve, typically the forward curve will show the yields on 1 year securities for each future year quoted on a semi-annual bond basis. So, typically forward curves would show the yields for 1 year securities. I have said it is usually 1 year, it is not necessarily 1 year, it may be 2 years, it may be 5 years, but the quotations are on year to year basis. So, 1 year 1 year initiation, 2 year initiation, 3 year initiation, whatever the maturity of the loan may be. So, relationship between spot and forward rates. Now, let me give you an example to illustrate this. Let us say I initiate a deposit with my bank today at t equal to 0 for a maturity of 3 years. I deposit an amount of money with the maturity of 3 years, and they gives me a certain interest rate. Let us call it S03. Let us say as an alternative, I make a deposit of 1 year right now with the perception, at least my mental perception, that at the whatever I get at the end of the year 1 year period, I will reinvest and reinvest it for another 2 years, so that I get a certain amount at the end of 3 years. Now, is it necessary that the interest rates that I get at the end, or the amounts that I get at the end of 3 years be the same, or is it necessary that no arbitrage would operate in this case? The answer is no. Why it is no? Because I am leaving the position in the second alternative when I am depositing the money for 1 year and keeping it open that whatever the interest rate prevails at t equal to 1 year, I shall deposit it for another 2 years as on that rate. Then I am exposing myself to the fluctuations in interest rate that would occur at t equal to 1 year. So, in that sense, the riskiness of the two legs of the arbitrage, say one is when I have already agreed on a certain rate, and that let us say that rate is riskless, the bank is the government of India, let us say government of India is a guaranteed bank, let us assume that. So, the payment on account of the 3-year rate is riskless, whereas in the second case whatever I get at the end of the first year I reinvest. So, now that reinvestment I have not fixed the rate at the point of reinvestment, and therefore, if the reinvestment rate decreases, my yield will decrease. If the reinvestment rate or the rolling over rate, rather the rolling over rate increases, I will get a higher yield. So, in this case the principle of arbitrage does not hold. The principle of arbitrage does not hold, because I have not fixed the rolling over rate, that is the rate at which I will reinvest the amount that I get at t equal to 1 in the second alternative. But what happens if that rate at which I am going to reinvest at the end of the first year is also fixed at t equal to 0? If that rate is also predetermined with certainty at t equal to 0, and just as I explained in a previous slide the concept of forward rate. Suppose I undertake a forward contract, I take a forward contract that at the end of the first year I will reinvest at this particular rate that is agreed upon at t equal to 0, and that agreement is default free. Then the arbitrage principle operates, because in both legs, in the first leg where I have straight away invested for 3 years, and in the second leg where I have invested for 1 year, but I also know with certainty the rate that I am going to get at t equal to 1 year for the future investment, then arbitrage would operate, and the amount that I would get at the end of the 2 years, at the end of the 3-year period, in both the cases, in both the alternatives, should be the same by the principle of no arbitrage. This leads me to the expression which is given here at the right at the bottom of the slide, 1 plus S03 to the power 3, which is on the basis of the spot rate at that I invest straight away for 3 years, one time investment for 3 years, and then the right hand side represents the rollover investment. I invest it for 1 year at a time, from 0 to 1 year, from 1 to 2 years, and from 2 to 3 years. But the important thing is the rates at which I invest at t equal to 1 year and then t equal to 2 years are already agreed upon or already prefixed and are default free and not exposed to any fluctuation, and as a result of which the risk in both the cases is 0, and therefore, the arbitrage process will mandate, or the phenomenon or the requirement of no arbitrage in efficient markets will mandate that we have this equation. The amounts that I get at the end of the 3-year period must be the same in both cases, and therefore, we must have 1 plus h 03 to the power 3 is equal to 1 plus h 01, which is the amount I get at the end of the first year investment, multiplied by 1 plus f 12, which is the amount that I get at the end of the second year, provided the rolling over is done at f 12, which is the forward rate agreed upon at t equal to 0 for a loan starting at t equal to 1 and ending at t equal to into 1 plus s to f 23, which is another forward rate which for 1 year, which starts at t equal to 2 and ends at t equal to 3. So, this is the no arbitrage. This equality is guaranteed by the no arbitrage condition. I shall continue from here. Thank you.